Last time we started talking about the connection between electricity and magnetism, and we started with talking about the force that a magnetic field applies to a moving charge and then therefore applies to wires, any kind of conductor with current flowing through it. Now we're going to move on to the next step, which is how moving charges, currents through wires, produce a magnetic field. And then sort of the last big step of this is we're going to see how changing magnetic fields can create an electric current. Then you have electric current causing a magnetic field causing an electric current, and that repeated pattern of electricity to magnetism is what electromagnetic waves are. And we're lucky we have electromagnetic waves because that's all light, and it's how all of the energy of the Earth comes as radiation from the sun. It comes through electromagnetic waves that are carried from the sun to the Earth. So this is a big topic, an important topic, and today we're going to talk about how a current-carrying wire produces a magnetic field. We're going to talk about two cases. We're going to talk about the magnetic field produced by a straight wire, and we're going to talk about the magnetic field produced by a coil of wire. All of these actually can be derived from a single equation, and it's called the Biot-Savart law. And we're not going to use this at all, so but I just want to write it down for you. So, I mean, really, more than anything, just so you can see sort of the complexity of it. Like, as you can imagine, it's difficult to use. And so instead of using the fundamental law, we're going to go to these two special cases. But this law says that the magnetic field that's produced is equal to a constant, mu sub 0, times the current divided by 4 pi, and then times this big integral that involves vectors. So the integral of ds crossed with an r vector, this r vector, you don't have to worry about what this stuff means, but this unit r vector divided by an r squared. And I'm not going to tell you what these different things are. I just want you to look at this integral form and imagine that in order to get from this integral form to the simple formulas we're going to see takes quite a bit of work, and we're going to skip all that work and just do the two cases. So the first thing we're going to consider is the magnetic field produced by current through a straight wire. This is going to involve a simple formula and then a right-hand rule for the direction, just like the stuff we did in the last lecture did. So the simple formula for the magnitude of the magnetic field is 2 times 10 to the minus 7. So that's like a constant. Times the current through the wire, divided by the distance from the center of the wire. So everything here is pretty self-explanatory, except that distance, that d, is the distance from the center of the wire to the desired point. Okay, that's the magnitude. What the? Computer glitches. 2 times 10 to the minus 7 times the current divided by this distance d. Okay, and then you have to think about the direction. And as with most or all of this electricity and magnetism stuff, it involves the right-hand rule. And so we're going to use the right-hand rule. Your fingers curl in the direction of the current around the loop. Your thumb points in the direction of the current through the wire. And then your fingers curl in the direction of the magnetic field lines. Okay, so if you have, let's say, I'm going to draw these first and I'll tell you what this means in a minute. So let's say that you have current flowing through a wire in this direction. This is the direction of the current through that wire. Then put your thumb in the direction of this arrow, and your fingers curl in the direction of circles that go perpendicularly around that wire. Okay? And so these are the magnetic field lines. If you draw a wire that's going, let's say the wire is coming out towards us. Okay, so that's the direction of the current. Put your thumb in that direction. The magnetic field lines go in the direction your fingers curl. So these are the magnetic field lines. Okay, let's put these together in an example problem. So let's say that there's a 20 amp current. And let's say that it's going into the page. And let's say we want to know the magnetic field vector at this point P, where these are 5 centimeters apart. So we want the magnetic field vector at this point P. Okay, first let's calculate the magnitude. That's the easy part. So this is the constant, 2 times 10 to the minus 7, times the current through the wire, which is 20 amps. I'll just leave off the units. Everything's SI units, like usual. The distance from the center of the wire to the point we care about is 0.05 meters, 5 centimeters. And so we get a magnitude of electric field vector at this point P of 8.0 times 10 to the minus fifth Tesla. And now we have to think about the direction. So point your thumb in the direction of the current. The current's going into the page, so put your thumb in the direction into the page, and you get something like, if this is your wrist, you know, you'd be looking at your pinky curling around like this. Your thumb's into the page. This says that the magnetic field lines are this way. Okay, so now we have magnetic field lines that are going this direction. We're almost to the answer for the magnetic field vector, but not quite yet. And so if this is the wire, the middle of this circle, and that's the field lines around it, you can imagine all of these, this is the entire field line that's at a distance of 5 centimeters from the center of the wire. The point we want is down at the bottom of that circle. And so the vector that's tangent to this field line in the direction of the field line is this way. So that's the direction of the magnetic field vector. And so I can write this as the magnetic field vector has this magnitude and it's in this direction. As usual, the easy part is coming up with the magnitude, and the more complicated part is using the right-hand rule correctly. The next case, the last case that we're going to deal with, is the magnetic field produced by current flowing through what's called a solenoid. And a solenoid is a bunch of coils of wire that share the same center. You just wrap this wire around and around. This is the way you make an electromagnet. To make a stronger electromagnet, you wrap these coils around a magnetic core. The key fact about, so why do we consider this case of wire wrapped around in coils? And the answer is that inside that circular loop of wire, the magnetic field vectors are constant, almost completely perfectly constant inside that coil. And so that's a really useful thing, to be able to produce a constant magnetic field. Okay, so if you have, let's say that your coil looks like this, but it goes around and around into or out of the page, then you have a constant magnetic field in here. The magnetic field is perpendicular to that coil, and it's constant at all of those dots. Okay, so what's the direction? I'll just draw it in this case, but if the current's going this way, these are all coming out of the page. And I'll put this in the notes in a second, but the way it works is pretty simple, really. Your fingers wrap around the coil in the direction of the current, and then your thumb points in the direction of the magnetic field. Okay, the magnitude, the easier part of calculating this, the magnitude of the magnetic field is equal to 4 times pi times 10 to the minus 7 times the current through the coil times the number of coils that you have, number of loops that you have, divided by the length L. And by the length L, I mean this. So if this is your set of coils, okay, you're looking at it from the side. This is the length L we're talking about. So in this case, if we were doing it for this set of coils, we'd have 1, 2, 3, 4, 5, 6, 7, 8 loops divided by whatever that length is. And for the direction, again, it's based on the right-hand rule. And make your fingers curl in the direction of the current through those coils. Then your thumb points in the direction of the magnetic field vector. So let me do a numerical example. Let's say we have current flowing through a bunch of coils of wire in this direction. Let's say that this current is relatively small, 1/100th of an amp. But let's say in this we have very tightly wound wire carrying this current. And we'll say that the number of loops is 5,000. And it takes up a space of 2 centimeters. And we want to calculate the magnetic field inside that coil. Then the magnetic field vector magnitude is 4 pi times 10 to the minus 7 times the current times the number of loops divided by the back to front length of those coils. So that's 5,000 divided by 2 centimeters. And you get a magnitude of 0.00314 Tesla. Now what about the direction? If you point your fingers, curl your fingers in the direction of that current, you have the back of your hand that you're looking at. So you're looking at your pinky there. Your thumb's going into the page. And so that's the direction of the current. Your thumb is into the page. And so the magnetic field vector is this magnitude into the page. Now we can combine this magnetic field that's produced by a current carrying wire with, put it in the vicinity of another wire that's carrying current. We know that any magnetic field applies a force to a wire with a current going through it, which means if you have two wires with current going through them, they apply forces to each other. Okay, you can do it one by one. Choose one of the wires, figure out the magnetic field it's producing, and then figure out the force that that magnetic field is applying to the other wire. Through the mechanism that we talked about in the last lecture, of the previous video, current carrying wires apply equal and opposite forces to each other. Okay, so I'm just going to go into two examples. So the first one is, let's have two parallel straight wires with the current moving in the same direction. Let's say the one on the left is a 10 amp current and the one on the right is a 15 amp current. So these are pretty big currents. And let's say that they run parallel to each other for a distance of 1.5 meters. And let's say that the distance between them is 9 centimeters. And the question is, what's the force each wire applies to the other? So I'm going to start by calculating the force that's applied to the 15 amp wire by the 10 amp wire. Okay, so what that means is we're going to calculate the magnetic field of the 10 amp wire at the distance away where the 15 amp wire is located. And then we'll go through the calculations that we did in the previous video in your last homework assignment to calculate the force. Then we'll switch the other way. Well, if you're a trusting person and you believe that these forces are equal and opposite, we can predict the force that the second wire is going to produce on the first wire. But if you're not such a trusting person, then you do this to verify it. But what we're going to see is that those forces are equal and opposite. Okay, so the 10 amp current, we have to figure out the magnetic field that it applies. It's going this direction. It has a current of 10 amps. So the magnetic field lines are going to be in the direction of this circle that I've drawn perpendicular to it. That's because of the right-hand rule. You put your thumb in the direction of the current and your fingers curl in the direction of the field lines. And so you can imagine that the 15 amp current is going through here. This is the field line that's 9 centimeters away from the wire. And so at the point where it makes contact with that 15 amp wire, the dotted red line, a vector that is tangent to that field line in the direction that it's moving is into the page. So that's what we know from this field line, is that the direction of our magnetic field vector at that point is going to be into the page. The calculation of the magnetic field says 2 times 10 to the minus 7 times the current of 10 amps divided by the distance away from the 10 amp wire that we want to be. That's 9 centimeters. And we get 2.2 repeating times 10 to the minus 5th Tesla. And like I said, it's going into the page. The hardest thing about problems like this is keeping track of which current you need in which equation. So just be very clear as you remind yourself. We're looking at the magnetic field produced by that 10 amp current. We're not thinking about the 15 amp current yet. And so that has to be the 10 amps. Now that we have that magnetic field vector, now we can forget about that 10 amp wire and just think about how that magnetic field vector affects the 15 amp wire. So now we're moving to thinking about the other wire. So the force vector is equal to the current through the wire we're considering now, the 15 amp wire, times the length of the wire that we're considering, that's 1.5 meters, times the magnitude of the magnetic field that we just calculated. Leave the units off. And this gives 5.0 times 10 to the minus 4 newtons. And we have to think about the direction of this force. Now we're thinking about that 15 amp wire. The current times the L vector. If you don't remember what that means, go back and refresh your memory from the last lecture, but that's this direction. That's the current times this L vector. The magnetic field vector is into the page. Now use the right-hand rule with your IL as your vector 1, your B as your vector 2, and your thumb ends up pointing in this direction. And so our final answer for the force vector on the 15 amp wire is to the left. Okay, so what that says is that the magnetic field produced by the 10 amp wire is pulling the 15 amp wire closer to it. Okay, it's a force vector to the left. Now, since these are equal and opposite, when we do the opposite calculation, what we expect to see is that the 10 amp wire is being pulled to the right. And so these two wires are being attracted to each other. Okay, so if these two wires have currents moving in the same direction, they're always going to be attracted to each other. Okay? So, opposites attract. That's not true with wires. They're looking for something with a current moving in the same direction that attracts. Okay, so now we're going to calculate, just because we're skeptical, we're going to make sure that these are equal and opposite by calculating the force on the 10 amp wire that's caused by the 15 amp wire. So first, let's think about the direction of the magnetic field lines that's produced by the 15 amp wire. We have 15 amps going this direction. This is the field line that's 9 centimeters away, so there's the red dotted line is the 10 amp wire. The magnetic field vector is equal to 2 times 10 to the minus 7 times, we're calculating the magnetic field produced by the 15 amp wire, so this is 15, and then we're dividing by the distance from the wire to the point we care about, which is 9 centimeters. And we get 3.3 repeating times 10 to the minus 5 Tesla. And now if the field lines are going in this direction, a vector that's tangent to that field line at that red dot is coming out of the page. And so that's the direction of the magnetic field vector. Now that we've calculated that magnetic field vector, we're done thinking about the 15 amp wire. Now we're just calculating the force this magnetic field vector applies to the 10 amp wire. So the force magnitude is equal to the current of the 10 amp wire times the length times the strength of the magnetic field I did this calculation wrong. I mean, you can just plug this into your calculator and you'll see that I wrote the wrong number in here, but this, no, I didn't. I'm sorry. So the magnitude of this force ends up being 5 times 10 to the minus 4 newtons. Okay, so the magnitude is the same as it was before. Now we just have to verify that the directions are opposite. Our current times our L vector of the 10 amp wire is going this way. Our magnetic field vector is going this way. Curl your fingers from the IL vector down to the vector coming out of the page, and what you get is that the force direction is this way. And so our force vector is 5 times 10 to the minus 4 newtons to the right. So the two wires are being attracted towards each other. And so the take-home message is currents that are directed in the same direction cause an attractive force between the two wires. Okay, I'm going to do a similar problem, but this time I'm going to have a wire passing through a solenoid, passing through a coil of wires with a different current. So we're going to have a straight wire that passes through a solenoid. And remember, this has to be perpendicular to it. and the solenoid has a diameter of 0.05 meters. Now, it's sort of an interesting fact that the diameter of the solenoid does not come up in the calculation of the magnetic field. Okay? The only reason we're going to need this is for once we have the magnetic field to figure out the length of the straight wire that's being affected by this magnetic field. That's why we need the diameter of the solenoid. Okay, so let's say that the directions look like this. You have your coil of wire going this direction. Let's say that the current is 0.02 amps. And let's say that this wire is passing through the middle, and this is a big wire with a 20 amp current going through it. Okay, and as far as the solenoid goes, the length of the solenoid is 6 centimeters. And the 20 amp current would be going into and out of the page, passing between two of those coils. And we're going to say that our N is equal to 50. And the question is, what's the force the solenoid applies to the wire? Well, first we have to calculate the magnetic field produced by the solenoid. So the magnetic field magnitude is 4 pi times 10 to the minus 7 times the current going through the solenoid times the number of loops divided by the length of 6 centimeters. And that gives 2.094 times 10 to the minus 5th Tesla. Now we have to use the right-hand rule for solenoids to get the direction of the magnetic field. Curl your fingers around so there's your thumb. That's hideous, but your fingers are curling around in the direction of the current. Your thumb is coming out of the page, and so the direction of this magnetic field is this way. And so I can write this as a magnetic field vector if I combine the magnitude with the direction. And now we go to calculating the force. So now we're done thinking about the solenoid. We have what we want from the solenoid, the magnetic field. The magnitude of the force is equal to the current through the straight wire, that's 20 amps, times the distance the straight wire is exposed to the magnetic field, that's the diameter of this coil, so 5 centimeters, times the magnetic field that we calculated, 2.094 times 10 to the minus 5. And we get a force of 2.094 times 10 to the minus 5 newtons. And now we want to get the direction. So the direction of the current times the L vector is this way. The direction of the magnetic field is this way. So use the right hand rule with your fingers curled around like this. Okay. Your fingers start out straight in the direction of IL and then curl around that way. And the direction of the force is up. And so we can think of this as the force vector if we combine the magnitude with the direction, and there's the answer. Now, what if I had asked what's the force that the straight wire applies to the solenoid? That would be a hard calculation to do directly, but if you're hopefully convinced now that these forces are equal and opposite, since the force on the straight wire is 2.094 times 10 to the minus 5 up, then the force the straight wire applies to the solenoid is 2.094 times 10 to the minus 5th newtons down, equal and opposite.